In this lecture, we will learn about carbon nanostructures. Carbon is one of the most abundant elements on the earth and forms the basic form of life. So, there are many polymorphs of carbon which are available, and eventually they go into forming nanostructures. So, we will learn about certain of those nanostructures which belong to that of carbon in this lecture. But before we go into that, we are more interested in what is nanotechnology, because carbon nanostructures, if we can somehow engineer them, we can tailor them to suit certain properties or certain application. We can make them as sensors, or we can also make them as reinforcing entities. We can also eventually get some data out of it, like we can make them as bridges between two entities, and we can pass the current through them, and we can again allow some properties to be measured from that aspect. So, that nanotechnology has emerged as a very strong tool because of this these nanomaterials. But nanotechnology, it comes out as a combination of not only engineering, but also some other sciences such as chemistry, biology and physics. Initially, the sciences were very different. In the case, we will go only with say physics, biology or chemistry, and engineering was supposed to be a different field of study, like making things work. But right now the paradigm is that everything is merging at a common podium. So, if I want to implant a chip in a body, I also need to see the physics of it, how those things will really make that happen. I also need to understand about how do I engineer it. It means how I can make that device work while it is in the body. Then I also need to understand the biological aspects of it. If it is in contact with blood, what do I do with it? So, now the paradigm of using this nanotechnology has merged all the disciplines, whether it is science or engineering. We need a common platform for working on that. So, that is how the nanotechnology has brought all the disciplines of engineering. It is not only about the material, but also about the mechanical and the electrical aspects as well. So, if that chip is being implanted into the body, it has to sustain certain forces or certain stresses. So, I need to design it using mechanical engineering. I need to design a material, I need materials engineering. If I want to pass some current into it, or I want to sense something, I also need to worry about the electronics of it, so that it does not degrade with time. In case I am also worried about releasing some drug using that particular device, it can be a material and I want to release some drug into the body, I need to have a very controlled degradation of that particular material. So, I also need to study about the biological part of it, that how much drug is to be released for a certain stipulated period of time. So, these aspects make things much more complicated, but now it has brought all the aspects to make this nanotechnology an interdisciplinary field of study. So, in nanotechnology, we are worried about materials which have very small sizes, order of less than 100 nanometers, and that has made it an interdisciplinary field of research. If I am worried about certain catalyst to release a certain drug, I also need to worry about the surface area of that particular catalyst. I need to worry about the rate kinetics involved in that. So, I am also worried about the chemistry part of it. So, there are many aspects which make things very complicated, and the subtleties are somehow ignored, or sometimes if I want to engineer it to that extent, I will also need to worry about those subtle aspects. So, that is how it has become a very complicated tool, and when I am using a nanomaterial, I need to also understand things at the nanoscale, because right now the bulk physics is very different than what you might expect at the nano level. So, again it is a very complex phenomena, and to engineer that we always need to worry about the nanotechnology. And again coming back to how small is nano, nano is nothing but any entity which is less than around 100 nanometers, and to see it visualize it physically, a nanometer is billionth of a meter, but it is about 1/80,000th of the diameter of a human hair. Human hair is approximately 100 to 150 micrometers in diameter, or this nanometer is approximately 10 times that of a diameter of a hydrogen atom. So, right now we are worried about 0.1 angstrom, that is a hydrogen atom, the diameter of that, and I am talking about scales 10 times than hydrogen atom. So, that makes it around 1 nanometer. We can see a human being, a human is generally a couple of meters, like 1.5 to 2 meters. So, that is the height of a human being, around 1.7 meter. An ant, it is approximately 1 millimeter, the length of an ant is approximately 1 to 2 to 3 millimeters. Then we have red blood cells which range in the order of microns, or 10 power minus 6 meters. And when we talk about a material, we find that a material has certain polycrystalline grains into it, and the grains also extend to the order of couple of micrometers. So, the grain size can vary from micron to submicron, and now we are worried about the microstructure of a material, and that approximates to the micrometer length scale. So, I am worried about micrometer length scale. I am talking about couple of micrometers, size of the grains. When I refine the grains to sub-micrometer range, less than 0.1 micrometer, then I am talking about something at nanometer level. So, that is what the range is approximately here, that I am worried about 1 nanometer or 10 power minus 9 meter, or that is approximately 10 times the diameter of the hydrogen atom, and that is what is nano. To give a physical sense, if a ant, if it starts holding a nano gear, so if I have an ant which is approximately 1 to 2 to 3 millimeter in length, and if it is holding a nano gear, that nano gear will be 300,000 times smaller than that, the ant itself. So, we can see an ant is approximately 10 power minus 3 meter, and we are going to nanometer, that is approximately 10 power 6 times bigger than a nanometer. So, that is what the overall feel of this nano length scale. Now, coming to the nanostructures. So, we can see that carbon has many polymorphs which are available with it. So, in this case we can see we have a diamond structure, we have a graphitic structure, we have fullerene structure, and then we have something called carbon nanotube. In the case of diamond, we can see we have sp3 hybridization. It means that each carbon atom is now attached to 4 other carbon atoms. So, we have one carbon atom which is now attached to 4 other carbon atoms, and that is what it gives a very strong strength, a very high hardness, a very high stiffness to the diamond. So, this is a diamond structure. So, each carbon is sitting at the tetrahedral, and it is now connected to the 4 carbons along therewith. So, that is why we can see that carbon can exist as a diamond, which is one of the very hardest known material, and that requires hybridization of sp3. Though we say that diamond is forever, but diamond is not the equilibrium form of a carbon. It is a graphite which is actually the equilibrium or the thermodynamically stable form of carbon. And in graphite we can see we have only one carbon is now attached to only 3 other carbon atoms, and fourth one is forming some van der Waals bonding with the layer which is beneath itself or above itself. So, we can see in this case we have sp2 type of hybridization in a graphitic structure. So, we can expect that conductivity or strength will be much higher along this length scale. So, we can see that we have free electron available, and that can basically hop, and in this case we can achieve very high strength. Why? Because in this case we have a covalent bond, whereas along the vertical direction I have van der Waals attraction. So, in this case in a graphitic structure I can get very high strengths along this horizontal axis, and apparently this van der Waals forces are pretty weak in comparison to that of covalent bonds. So, I can easily slide these 2 layers, and I can basically slip those graphitic planes over each other, and that gives the overall lubricating property to the graphite, whereas that thing is not possible in the diamond structure, because diamond structure it has all the bonds which are covalent. So, that is a problem in diamond, but we can get very good lubrication in this graphitic structure, because we have a van der Waals force which is joining the two layers of graphite. So, that's what defines the overall graphitic structure. And then we have something called fullerene. This is also known as Buckminster fullerene, which is on the name of Buckminster Fuller, Buckminster Fuller, which has actually developed this structure of geodesic dome, and based on his structure, this structure was dedicated to him. Now, coming to CNT, this is nothing but a single layer of, when a single layer of graphite is rolled into kind of a tubular structure. So, we can see a tubular structure is made, and that basically is forming a diameter which is approximately much less than 100 nanometer. So, that is why we are calling it carbon nanotube. It is a hollow structure, that is why it is a tube. So, I am taking a layer of graphite and I am rolling it in a manner that I get a tubular structure, and that is called a carbon nanotube. So, carbon nanotube are nothing but long and thin cylinders of carbon. It was initially discovered by Sumio Ijima in 1991. That actually popularized the application of carbon nanotubes in the nanotechnology. So, we can see there are a couple of nanostructures. We also have a structure of amorphous carbon. So, again that part we will not be covering out here, but again we have also have amorphous carbon which can also exist as one of the allotropes of carbon, which are very widely used are diamond. So, diamond is sp3 hybridization we can see, and it is one of the very hardest known material and very high thermal conductivity as well. Then we have graphitic structure, it is very well used as a lubricant, and it is sp2 hybridization, where along this layer thickness, along the layer we have covalent bonds, whereas along the vertical direction the interaction between the two layers is through van der Waals forces, and these bonds are weak, so they can easily glide over each other, and when a certain stress is applied. So, it can be a very good lubricant. Then we have fullerene structures. So, that is composed of certain pentagons and hexagons that complete the soccer ball type of a structure. And then we have carbon nanotubes. Carbon nanotubes are nothing but very long and thin cylinders. So, we can get aspect ratios which is nothing but the length to the diameter ratios as high as 1000 or more than that, and that was discovered by Sumio Ijima in 1991. So, that is what we can see the overall how the carbon nanostructures are being developed. The first thing is graphene. We learnt about graphite, but graphene is nothing but a single layer of graphite. So, we are talking about only a single layer which is present in the graphite, and that constitutes the overall graphene, and we can see the overall hexagonal structure which is predominant in the graphene layer. So, that is what we can see out here, that we have this hexagonal structure which basically develops in the graphene. So, we can see that we have a single layer of graphite, and that is called a graphene. The beauty of this one is that it has a very high thermal conductivity, as well it has a very high strength. The fracture strength can be as high as around 200 gigapascals, whereas the modulus can be as high as 1 terapascal. So, that is what we are talking about graphene. Apparently, graphene has very high transparency to the order of 97%, which can be utilized for making transparent screens out of it. Can absorb as much as 2.3% of the incident radiation, and that is what makes it very special, because if you are depositing this graphene by a single graphene layer, we can really see the change in the opacity, and if we have two layers, that will be much more opaque. So, even we can detect this opacity via our naked eye. If we go about characterizing it, because to see a nano layer we need very sophisticated tools such as TEM or something like that at the order of electron microscopy. So, but if we just deposited a single layer of graphene, we can just observe it using this our naked eye. So, that is the beauty of this graphene structure. So, it can be utilized for blocking the radiation whenever it is required, at the same time providing a very good conductivity. So, that is what, because the single layer of graphene is very highly conductive as well, and its conductivity can go as high as maybe more than 100, around 100 times that of a 10 to 100 times that of a silver or copper. So, it can be highly conductive as well. So, that is the beauty of this graphene layer. Apparently, a group in the Maryland at College Park, they have isolated a single layer of graphene, and then what they have done, it is approximately 1 micrometer wide, and they have sprayed them in a vacuum chamber, and they held it in mid air by using some electric fields. So, once it is being held in the electric field in vacuum, it is kind of floating, and after it is floating, they have applied magnetic fields, and then from that they have seen the rotation of this or rotation of this graphene, and it can rotate as high as 60 millions RPM, that is highest ever observed. So, it means that graphene layer or that graphene particular layer is rotating at a speed of 60 million RPM. So, it is rotating in that speed. Apparently, if I try to rotate anything even at say 30,000 RPM or 40,000 RPM or even 1 lakh RPM, it will start heating up like anything. Whereas this graphene layer does not heat up, it is still stable at 60 million RPM, and it is actually been proposed that this is not the top speed of this graphene layer. So, we can make very wonderful things out of graphene without letting it disintegrate. So, that is these are the recent applications which are coming in this particular arena. So, graphene is one of the very fascinating materials, and if you want to rotate it like using some magnetic fields, you can make certain rotors or motors out of it, and from that we can generate very high power as well, and they can go speeds to the order of 60 million RPM without even disintegrating. So, that is what is one of the applications of these graphene layers. Now, coming to fullerenes. Fullerene, again, it is nothing but a geodesic dome type of a structure, where you can see that you have a truncated icosahedron. So, it appears more like a soccer ball. So, you have a structure which is a kind of a soccer ball, and it has around 20 hexagons and 12 pentagons, which gives the overall curvature. Because if you have only hexagon and you rotate it, it will form some sort of a tube, not really a ball kind of a structure or a sphere kind of a entity. So, you need to have pentagons to give it a curvature, and that is what is happening here. And all these pentagons are not really joined with each other, they do not share the edge, but it is being shared through the hexagon. So, we can see we have hexagons out here, and that thing is being joined by a pentagon. So, that is what we can see out here, hexagon, then again we have a pentagon. So, we have pentagon, hexagon, pentagon, hexagon kind of a structure, and that is how it is being joined to give it a curvature. So, that is the beauty of this particular fullerene structure, and it is being named on the Buckminster Fuller, and who had popularized the geodesic dome structure. So, fullerene is again one of the polymorphs of the carbon. It has a structure which is a truncated icosahedron. So, it appears more like a soccer ball, and it has around 20 hexagons. It has 20 hexagon and 12 pentagons to give it this kind of a spherical structure. There are other entities also possible like C20, C70 and so on, but this is the one which was initially been discovered, and it was basically named on Buckminster fullerene. It is also called a buckyball structure, and to shorten the form, it is called as to shorten the form of Buckminster fullerene, it is called as a fullerene only. As I said earlier that the carbon nanotubes were discovered in 1991 by Sumio Ijima, but these CNTs or the carbon nanotubes were discovered, they have been actually named as carbon filaments even as early as 1952. That is what we can see here. So, the transmission electron microscopy of these carbon nanotubes were mentioned as early as in 1952, maybe like 40 years before, in Journal of Physical Chemistry of Russia. But these findings did not come to limelight during that time, because there was a cold war going on between Russia and America, and also there was a problem of access to the Russian scientific publications, and also the language of Russian was not that predominant during that time. So, that is the reason that this finding did not emerge even till very late. So, this paper was written by Radoskovich and Lukyanovich in 1952, and they mentioned them as carbon filaments and not as carbon nanotubes. So, that was the earliest finding of carbon nanotube. Even later on, the filamentous growth of carbon was again being mentioned by Oberlin and Endo and Koyama in Journal of Crystal Growth in as early as 1976, and they had told that they can form this filamentous carbon by pyrolysis of benzene, and they were more worried about the carbon fibers, which also incidentally contained a hollow tube. So, now we have gone from carbon filaments to filamentous growth, which is also showing a hollow tube with a diameter approximately of 2 to 50 nanometer along the fiber axis, and again they have also formed an annual ring of structure of tree. So, that is what we are they also mentioned, that by the pyrolysis of benzene at around 11 degree centigrade, they can form carbon fibers which with the presence of some hollow tube which is a diameter of around 20 to 500 angstrom, that means 2 to 50 nanometers along the fiber axis. But again these findings also did not come to limelight as such. Why that thing happened, that now the discovery of carbon nanotube is dedicated to 1991 to Sumio Ujima. Because first thing was in 1952 the Russian journal were not that accessible, the Cold War was going on and those Russian publications were not available to everyone, and again the Russian language was also not so popular. In 1976 again they talked about this filamentous growth of carbon, but the problem is that time they were studying about avoiding this formation of this filamentous carbon in certain areas, certain regions. It was some mineralization was some process was going on and they wanted to remove the formation of this filamentous carbon, and they were more worried about how this growth is occurring and all that. At that time the nanowave had not come. So, that is one of the biggest thing which really came into that, and all this investigation was based on some growth mechanism, and that was not so interesting for the physicist. Even the maturity of science was not there, and they were not able to think nano during that time, because nano was popularized much later in 1980s and 1985. So, that nano wave had not caught in the people, and since they are worried about the growth of this filamentous carbon where they want to avoid this formation, this did not really interest the physicist. Whereas, in 1991 this paper was published by Sumio Ujima in Nature, and that is read by all kinds of scientists, academicians, which will involve basic research and fundamentals, and physicists read them very easily. They are very widely read by physicists. So, now that nanowave had caught, now people are more aware of what is happening around the world. It was written in English and it was read by all the physicists. Nanowave was catching up, and the term he had coined, it was carbon nanotube. Now it had caught the wave because it was published in Nature, written in English. It is accessible to all the physicists, and it is being read by matured scientists because the science has developed to that extent, and that basically popularized the discovery of carbon nanotubes. So, though we can see that a filamentous carbon was forming in as early as 1952, later on it was again reported in 1976 that they are observing growth of hollow tube kind of a structure, and apparently all these two journals 1952, 1976, they also have reported TM images, transmission electron microscopy images showing the filamentous carbon, but still it got popularized only in 1992 by Eveson and Ajayan, who coined the term carbon nanotube in their Nature paper. So, that actually created the way, and that popularized the application of carbon nanotubes for basic research as well as for further application. Apparently, the carbon nanotubes, they have a hexagonal lattice. So, the lattice goes like this. So, it is a symmetric hexagonal lattice, and then so we can see that kind of lattice which is forming in the hexagonal, that is nothing but the graphitic layer of carbon nanotube, and the distance between carbon to carbon atom is approximately 1.421 angstrom in graphite, but because of curvature there is a increase in this particular bond distance between carbon, and that comes around 1.44 angstrom. That is a better approximation what researchers generally use. This can go even higher when the curvature, depending on the curvature. So, that is what is being that is what is basically being accepted as a value for this bond length between carbon in a CNT structure. So, we have CNT, it is a hollow tube. So, higher the curvature, higher is the stretching between the bonds. So, once you have a flat layer, if you can cut them up, it will be in equilibrium, but once you start putting the curvature, the bond length between the carbon will start increasing. So, if you can define a chiral vector, and we can also compare it with the Cartesian coordinate, it can go like this, that chiral vector we have something like this going along this direction, and second entity which is going along this direction. So, we can see that we have A1 along this direction, A2 along this direction, and then we also want to define it using a Cartesian coordinate. So, if I take this one as a origin and I want to define it using Cartesian coordinate, I will take, let me just change the color of the pen. So, I can, so if I take this as origin, I will take it as x and I will take this as a chirality or chiral vector is defined as the direction along which if tube is rolled, that becomes its circumference. So, the chirality can be given as n times A1 plus m times A2, where A1 and A2 they are nothing but the vectors of the hexagonal lattice. So, they are around two vectors with around 120 degrees of opening. So, that is what is A1 and A2. So, we can see that A1 and A2 will go along this direction. So, they will have around 120 degree of opening with them, and using the Cartesian coordinate I can define A1 is equal to 3 by 2 times ACC, where ACC is the bond length of carbon, root 3 by 2 AC, and then your A2 can be given as 3 by 2 ACC minus root 3 by 2 ACC. So, we can see if it has to traverse. So, I need for A1 I need to traverse along x, I need to travel 3 by 2 times of the bond length, and along y I need to traverse root 3 by 2 of bond length of carbon. So, that is how I can go from here to here. So, I have to traverse along x I traverse some distance, along y I traverse some distance. So, this is x, this is y, and that gives me x and y in the Cartesian coordinate. Apparently, if I take its chiral vector, so chiral vector is nothing but n times A1 plus m times A2, and that comes out to be, so CH, that is a chiral vector, that comes out to be root 3 bond length of carbon n square plus m square plus n m. So, we can see that the Cl is the circumference of this tube, or which is defined as the chiral vector for this particular carbon nanotube. So, that is how it is coming out for the carbon nanotube. Apparently, we can define carbon nanotubes in two certain forms. So, once I come to that, I will also discuss how we can really form it. So, let me first go back to this carbon nanotube structure, and then let me explain it further. Let me say it that for armchair we have n equal to m, and for zigzag my m is equal to 0. So, for armchair my chiral vector becomes, when m is equal to 0, sorry, n equal to m, I can get root 3 ACC n square plus n square plus n square, that becomes root 3 again. So, root 3 n square, I get 3 ACC n. So, that is what my chiral vector is for armchair. The chiral vector is 3 times n multiplied by ACC. For zigzag structure my m is equal to 0. So, chiral vector becomes root 3 ACC multiplied by n, because m is 0 and m is also becomes 0. For zigzag my chiral vector is root 3 ACC multiplied by n, whereas for armchair my chiral vector is 3 ACC multiplied by n. So, there is only difference of root 3. So, now if I can see how a zigzag structure will look like. So, for zigzag m is equal to 0, for armchair m is equal to n. So, if I get this lattice of carbon nanotube layer, Okay, so something like this. So what I am getting is, okay, let me just again change the color so I can give it a better feel. So let me start with here. So if I am traversing along this side, I am getting 1 0, 2 0, 3 0, 4 0 and so on. If I am traversing at the 30 degrees, what I am getting is I am getting to this point, this becomes my 1 1. I go from here to here, becomes my 2 2 and so on. So, if I am traversing along this side, what I am finding is this is, okay, if I am traversing along this side, my m is equal to 0, it is forming my zigzag CNT. If I am traversing along here, this is my 0 0, I am traversing along here, I am getting a armchair kind of a thing. So, in zigzag I can see I can get this sort of a traverse, whereas in armchair I am traversing like this and I see this sort of a structure. So, that is what I am getting, that I am traversing here, I am seeing something and then again I am coming back to this. So, I have a repetition of from here, I have a repetition of something like this. This is forming my armchair and whereas this one is forming my zigzag. So, we learned that the chiral vector for zigzag, it was root 3 n ACC. For armchair, the chiral vector was 3 times n ACC. So, depending on the n, that is the vector which has been traversed along on a particular side. So, n is along direction x and along A1 and m is along A2. So, that part we can see here, and from that we can and chiral vector is nothing but it is kind of a length which has been traversed that forms some sort of a diameter, or sorry, the circumference, diameter multiplied by the pi, that forms the circumference. So, that chiral vector is something like a circumference of that particular tube. So, when I have this type of structure, I can always find what is the approximate diameter of the tube, because that diameter multiplied by pi will give me the chiral vector. So, that diameter is equal to 3 times n ACC divided by pi for armchair, and d is equal to root 3 n ACC by pi for zigzag. So, from this, from the chiral vector, I can always identify what is the diameter of that particular entity. So, if I want to find a zigzag, I just need to roll them along this particular direction. So, depends, I will just show you the examples of zigzag and the armchair configuration. Apparently, I can also find the theta, that what theta I am rolling this particular entity. So, for armchair, theta is equal to tan inverse of root 3 m by m plus 2n, and in this case m is equal to n. So, what I get is 1 by root 3 tan inverse of 1 by root 3, that is equal to 30 degree for armchair. For zigzag, my m is equal to 0. So, I get theta also equal to 0. So, just couple of things, that in zigzag I get this kind of a morphology, that I go up, go down, go up, go down, that is forming a zigzag, and chiral vector is given by root 3 n ACC, whereas armchair I see I traverse, I go up, traverse, come down, and that is forming a armchair, because that is more like sitting on a chair with a arm rest on that is why it is called armchair. And chiral vector is nothing but some sort of a circumference which is being achieved in the structure. So, I get chiral vector, I can relate it to the diameter of that particular carbon nanotube, and from that I can get the overall diameter. Apparently, the theta at the angle at which I am rolling it to get this particular nanotube, that can also be achieved using this particular relation. And for armchair, it is 30 degrees. So, the theta value I am talking about is that theta is 30 degree with respect to the Cartesian coordinate, and that thing is 0 for the zigzag, where it is around 30 degree for the armchair. So, now let me show you how these structures look like. So, we can see that once we have a graphitic plane, the way we roll it, we can achieve either armchair, chiral or zigzag type of a carbon nanotube. So, in case when we have a armchair, we have theta of 30 degrees. So, we have 30 degrees theta when we have armchair, and in zigzag we have theta of 0 degree. So, depending on that, it just matters on way we define it. So, we have 0 degree out in zigzag and armchair is around 30 degree. So, we can see that the nature or the electrical nature of this one can be very different, like in zigzag it can be highly metallic, in chiral it is a semi metal, and in armchair it is a semi conducting. So, depending on that, the way we are rolling it, we can achieve different type of conductivities in the carbon nanotube. So, that is what we can see out here. Generally armchair, we have everything is semi conducting, chiral it can range from semi conducting to metal. So, once we have this relation, when 2n plus m is an integer multiplied by 3, then we get something which is metallic. In other cases it is generally semi metallic. So, if we can roll it, so if the rolling is like this, so this particular part will be metallic, whereas this part will be semi metallic, semi conducting to metallic. So, along this side it will be metallic, and that basically corresponds to the zigzag structure or the 0 direction, and in this corresponds to the armchair type of a fabrication, which is nothing but semi conducting to metallic. And carbon nanotubes, they exhibit well defined perfect crystal, which is a covalent carbon to carbon bond, and again this graphite is now rolled into various ways. So, I can roll it like this, I can roll them like this to get this armchair type of configuration. In that manner I can roll it to get a zigzag kind of a structure when I roll them along 0 direction, and then again I can so basically I am joining this end with this end to get this armchair. If I can roll them like this, so I can see that these things will come at the end, the extreme ends will come at the end, and if I am rolling it like this, I am getting zigzag, and if I am rolling them in any other direction, then I am getting this chiral type of a structure. And these properties, they are very different basically along different directions. So, apart from the conductivity, so conductivity can be very different along armchair or zigzag, whereas other properties like if I want to reinforce them, that also will depend on the covalent bond, strength of the covalent bond. So, that will depend again which is essentially the same in all the 3 cases, because I again have covalent bonds along the length of the tube. So, I can get pretty much very uniform properties along this side, and also they are much uniform along the cross section of that as well. So, depending on where I am loading it, if I am loading it along this side, I might get very high properties, whereas in other case transverse direction it might be different. So, why do we want to use carbon nanotubes? Its current density can be 1000 times higher than that of copper, because there are no problems associated with the electromigration as in case of copper. But this does not mean that the carbon nanotube also have lower resistivity than that of copper. We can see that the carbon nanotube has resistivity to the order of 10 to 50 micro ohms meter, whereas that for copper it is 0.01 micro ohms meter. Even if I am conducting silver, it is approximately around 100 times than that of a silver. It can be utilized in microelectronics such as cathode ray lighting elements, CRT, flat panel displays, nanotube transistors. The idea is that what we achieve in a LCD is we have some sort of pixelated picture, and each pixel has certain dimension. So, because each pixel will give us certain color, and that will eventually produce some picture which we are looking at with different colors. If we can replace all these pixels by CNT, so the diameter of CNT is nothing but couple of nanometers. So, if we can replace them by a CNT, I can get more number of pixels in the similar area. So, eventually what I am getting? I am enhancing the resolution of the screen. So, it will appear more like I am watching face to face anything, and I am not, it will appear very much, it won't, the picture will not appear pixelated, but it will appear like I am watching someone face to face, and that will produce the clarity in a picture or in a particular display panel. So, that is the idea behind using carbon nanotube. Also, carbon nanotubes are also being utilized for energy storage, because it has a hollow structure, it can store hydrogen very easily, and it can be utilized for the application in fuel cells. Also, for nanoprobes and sensors, if the sensor is the smallest possible entity, then I can detect that much. So, that particular sensor will be that much sensitive to grabbing or detecting a particular species. If my sensor itself is very big, it will require very high concentration of that species to be able to detect. So, these carbon nanotubes are very small entity. So, they can be used as a nano probe, and they can also sense it very easily. So, I can achieve very high resolution. That is the advantage again with using CNT, which are nanometer, they have nanometer diameter, nanometer length diameter. They can also be utilized for very high strength applications. So, if I can somehow reinforce a material such as polymer or a metal matrix with carbon nanotubes, I can achieve very high strength as well. So, again CNTs have very wide applications, like in electronic novel electronic applications, because of their high conductivity. In microelectronics, again in energy storage it can be utilized. I can also utilize them as nanoprobes and sensors to collect a particular signal from a particular species. It can also be utilized for enhancing the strength of the composite. Again, it can also be utilized for some biological applications. So, the applications of CNTs are just plenty in number. So, applications of CNT are basically utilized for enhancing the strength in polymer matrix, enhancing the modulus again in the metal matrix, but in ceramic matrix the modulus is pretty high already, but what they lack is nothing but the toughness. So, in polymer I want to utilize CNT for enhancing the fracture strength, enhancing the modulus. In metal matrix I have enough toughening available, but I want to enhance the modulus or fracture strength, and in ceramic matrix I want to enhance the toughness. But the problem with CNT is that they have very low surface energy, because there are no bonds available for it to bond with anything. So, we want to somehow break the bonds of this carbon to carbon and then make some bonds available for reacting with the nearby species, that is nothing but polymer or metal. So, once we are breaking the bonds of carbon and we are attaching some additional molecules, we call it functionalization. Functionalization, it means we are breaking the bonds of carbon, those graphitic bonds, we are allowing one bond to basically tangle out and then give out a additional bond which is available for bonding with the interfacing species. It can be polymer or metal, and that is what we are interested in. But that if we are damaging this carbon bond, then there will be some damage to the carbon nanotube itself. So, I can have single layer of carbon nanotube, a single layer of graphene, and then I can roll it to form a single walled carbon nanotube. If I am damaging the structure, basically I am deteriorating the properties. So, I may want to go for a double walled or multi walled carbon nanotube. It means I am taking a multiple layers of graphene and then I am rolling it to form carbon nanotube. So, even when I damage the top layer, I still have some layers available beneath that to take care of the additional load or to deliver the stress. So, that is what is certain design criteria which need to be considered for designing the carbon nanotube based composites. So, they can be utilized in polymer matrix, metal matrix or ceramic matrix, and the utilization of CNT is very different in all the three cases, because in polymer I am more interested in reducing the density as well and also enhancing the fracture and the modulus, In metal matrix, I again want to enhance the modulus and fracture strength. In ceramic, I want to enhance the toughness. So, how do I basically enhance the strengthening? I can utilize the higher elastic modulus of carbon nanotube, that is to the order of 1.4 terapascals, which is very high. Fracture strength can be as high as 200 gigapascals. Also very good bending strength, but advantage is that carbon nanotube, they can bend completely. So, I have carbon nanotube, and if I apply certain stress to it, certain load to it, it will basically bend completely without breaking. So, it can just bend completely without breaking, and that is the advantage of it because of its high strength. At the same time, it will not fracture. So, it will not fracture. So, it can absorb very high energy in terms of bending. So, its stiffness also is being utilized, and its modulus also is being utilized in delivering the bending strength to a particular composite. At the same time, it has very high specific strength because of its low density. So, because of low density of CNT, if I are dispersing them in a particular matrix, it can also yield very high specific strength, or the overall strength. It can be fracture strength, yield strength, it can be basically be enhanced because of presence of carbon. Apart from that, we can also achieve toughening, specifically in ceramics. I can achieve toughening by carbon nanotubes by crack deflection. So, if a crack is progressing, I can always have some CNTs to disallow the propagation of crack along this direction, and it will have to change its direction. And once the crack direction is changed, it requires additional energy to propagate. So, because now it has to go again in this direction, so the energy required to change its direction is pretty high. So, CNTs, they act as obstacles, and they help in absorbing extra energy. That gives rise to crack deflection, and crack will not really propagate through them because of their high modulus and high strength. So, it will not be able to fracture carbon nanotubes right now. So, in that case, we can achieve crack deflection. So, instead of crack propagating straight, it has now contoured path, and that results in the enhancement of the fracture toughness, enhanced fracture toughness. Second criteria is crack bridging. In crack bridging, what is happening? If a crack is trying to propagate, and I supply, crack is trying to propagate along this side, but then I have a carbon nanotube which is present between particle A and particle B. So, it will not allow the crack to propagate further, because I have a bridge kind of entity which is out there. So, for crack to propagate, these two entities have to go apart, but because of CNT, it is holding the two particles together, or the two structures together, the two surfaces together. So, crack will find very hard to propagate further, because it does not have the space, it can't make these two things go apart. So, in the process, this is called crack bridging. So, I have crack which is being bridged by the carbon nanotubes. So, that is second way of toughening, it is called crack bridging. And third thing is crack CNT pull out. So, in this case, once it goes to an extreme, I can also get CNT fractured. So, if I had a crack like this, when some excessive load is being applied, these might start fracturing. So, I have carbon nanotube and I am applying loading like this. So, it can eventually fracture some of the carbon nanotube, but CNTs have very high strength, they have very high fracture strength. So, it is now absorbing extra energy. Ideally, that energy would have gone to enhance the crack length, but now that has gone in fracturing the carbon nanotube. So, eventually the crack length is much shorter than what it would have been in absence of carbon nanotubes. So, in presence of carbon nanotube, it is just restricting the flow of crack in that particular direction. So, we can see carbon nanotubes can enhance the crack deflection, they can cause crack bridging, it can also cause CNT pull out. So, by all these three processes, it can render a toughening to the ceramic. So, in crack deflection, the crack has to change its direction, so it will not be able to propagate. In crack bridging, we still have some carbon nanotube left between the two surfaces, so it will not allow it to go further apart. In CNT pull out, we are using some energy to fracture carbon nanotube, and since carbon nanotube has very high fracture strength or yield strength or even the bending strength, that energy is now being utilized in fracturing CNT rather than fracturing the composite. So, what is happening? That overall crack length is now very short. It has now a very shorter length in comparison to what it would have been in absence of carbon nanotube. So, that is how we can get different sort of toughening by the presence of carbon nanotube. Second thing is the wetting of carbon nanotube. If I want to wet carbon nanotube, because all the surface it is very low surface energy, because there are no free bonds available for anything to sit on this particular material. And if I have a ceramic material and I want to make it a stronger bond or a metal with a stronger bond with it, I need to melt that particular metal. So, that creates a difficulty in modeling, because to melt a metal or to melt a ceramic, I need to go to the melting point plus some additional temperature to cause the wetting of the carbon nanotube surface. So, I have a melt of say ceramic. So, that becomes very difficult. So, I need to take this melt at very high temperature so that it can cover the carbon nanotube. Again, the role of roughness. So, CNTs can also impart roughness to the structure, and in that case it will affect the overall wetting. What is happening is I have carbon nanotube on the surface, and if I put some droplet of water, it might just stay over those carbon nanotubes because they can support the water droplet, because there are plenty in number, without letting the water to get into the grooves, because it will require very high pressure for the grooves to be filled in. A datum of around 3 to 10 meters might be required to fill in the cavity, which is approximately 1 micrometer apart. So, that is what it tells, that role of roughness can be very critical. I can change the overall surface properties, I can change the wettability, I can make it highly super hydrophobic. Second thing, I can also enhance the overall catalytic property in terms of absorbing or detecting a certain species. So, that is how I can really alter the overall specification of the surface characteristic by adding roughness to the composite. So, those are all things which can happen in this case of carbon nanotube. Again, CNTs are they are being discussed as toxic as well as biocompatible. Why? Because toxicity is of a concern when I am using carbon nanotube in a particular biomaterial. There are two schools of thoughts. First thing is that anything in the nano form, because I am talking about carbon nanotube. So, anything in the nano form, it is anyway dangerous, because if those particles get into the lungs, it will be very hard for them to come out, can't come out. So, they might cause some problems of the lungs, and it can like it is more like silicosis, that silicon gets deposited into the lungs and it can't really come out. But on the other hand, there is second school of thoughts which says that carbon is the basic form of life. So, anything which is carbon should not harm the functionality, because carbon is the basic form of life. And once this carbon nanotube is being reinforced or being trapped in a matrix, it is no more available as a free form. So, then it cannot be toxic. So, it is non-toxic, but people still do not know what will happen if CNTs are available in free form. They might get deposited into either the lungs, kidney, liver or heart, or they might even go to the brain and cause some damage. So, CNTs in free form might be dangerous, but once they are being entrapped in a matrix, then they might be much more biocompatible. And apparently, there are some researchers who have also shown that once we have a CNT carbon nanotube, it can also allow the precipitation of apatite. Apatite is nothing but the mineral part of the bone. So, people have seen that, researchers have seen that the apatite can really grow on the carbon nanotube as well. So, carbon nanotube surface can also act as a surface for precipitation of apatite crystals. So, that is again which are certain concerns which are associated with the carbon nanotube in terms of their toxicity or their assistance in precipitation of apatite. So, again this has to be handled with extreme care when a biocomposite or biomaterial is being developed. So, in summary we can see that nanotechnology is basically an interdisciplinary field of research which involves science as well as engineering. Then we learnt about this carbon nanostructures polymorphs, specifically the graphene layer, the graphite, fullerene and nanotubes, and we concentrated on basically the nanotubes in terms of strengthening and toughening the matrix, and also learning about how the wetting can occur in carbon nanotube and why it is very essential. Because I can impart a different functionality to the biocomposite or that particular composite, and then I am also worried about the biocompatibility because I want to utilize their strength for enhancing the toughness of a ceramic, that is the apatite. So, whether it can be utilized as a biocompatible material, that is again it requires much more research before anything can come to a conclusion, but definitely once they are being incorporated in a matrix, they can be used as a reinforcing or strengthening agents. So, with this I close my lecture. Thank you.